Hi and welcome to Maths class. Today we're looking at the fundamental theorem of calculus. Now, before you hear the name and freak out, it's got such a fancy sounding name, not because it's tricky and hard to understand, but because it's so useful and it enables mathematicians to do so much, right? So it's important, but that doesn't make it hard. It's actually fairly straightforward to use. And so what we're doing in this video is we're just going to look at how to use the fundamental theorem of calculus, and we're looking at what it means. There will be a video to follow this which will go further into the theory to prove why it exists and why it's true. But that's the next video, and we're going to start here. Okay, so the fundamental theorem of calculus states that if f is continuous, if f is a function that is continuous on an interval from a to b, then this is true. So this is the interval from a to b, and these are called my terminals. There's my function f of x dx. So this would be the general integral sign, but when I put these terminals in, then it becomes capital G of b minus capital G of a. So what is this G? Where does it come from? G is a function which, when I differentiate it, I get f of x. In other words, G is an antiderivative of f of x. Now remember, when we find a general antiderivative, we have a plus c. But because of this subtraction, the c's get cancelled out. So I don't need a plus c for G. So when I say G is any antiderivative of f of x, usually what we then do is we can antidifferentiate f of x without putting in a plus c. Now, for my notation, to help me calculate the actual value, because a and b are typically either numbers or constants that will need to be substituted here. So the first step of my working, what I do is I anti-differentiate to find out what capital G of x is, and I write it in these square brackets with the terminals a and b written at the corner like that. We're going to do an example in a minute and you'll see what that looks like. I'm just going to go through a few properties of the definite integral. This is called the definite integral. The first is that when my terminals are equal, then this is all going to equal 0, because I'm going to be doing G of a minus G of a, which will be 0. The second one is, if I've got a point in between a and b, and let's call that point c, then if I needed to, I can break up this integral into from a to c plus from c to b, as long as, that's not very clear, a is less than c is less than b. So c is a number in between a and b. My third property is that if I have a constant k in front of the function here, I can bring the constant out in front. We've seen this before, it's not new. My fourth property is that if I've got two functions added together, then I can calculate them separately and it'll give me the same answer. My final property, I ran out of paper there. My final property is that if I reverse the terminals, instead of going from a to b, I go from b to a, I'm going to get the same answer but negative. And that makes sense because basically this is going to be g of a minus g of b, which is the negative of g of b minus g of a. All right. So we've been through the properties. The next thing to do is look at an example. So this is how it goes. I'm going to evaluate from 1 to 3 of 3x squared plus 4x minus 1 dx. So take note not only of what I do, but also of the notation that I use. So in my first line, I'm going to use square brackets, and inside the square brackets, I'm going to put an antiderivative of this function. So 3x squared, I'm going to increase my power by 1 to give me x cubed. Then I'm going to divide by the new power. So it'll be 3x cubed over 3, which is just plain old x cubed. 4x squared, if I raise the power of x, increase the power of x by 1, I'm going to have x squared, and then divide by that 2, which will give me 2x squared. And then a constant term, I'll just multiply my constant by x. So I'll have negative 1x, which I just write as minus x. So at this stage, I don't need to write in a plus c, because if I did, I would end up subtracting it and it would cancel anyway. So I close my square brackets and I write down my terminals 1 and 3. The next step is substitution. So this is going to be this function when x is 3 minus this function when x is 1. So I'll do that on the next line. I'm going to do a direct substitution. I get 3 cubed plus 2 times 3 squared minus 3. And now I'm going to subtract the whole thing. So what I want to do is subtract and open brackets. Don't try and get smart and skip a line. You'll only make a mistake maybe 10% or 5% of the time. That's too often, right? Just write your subtraction and open brackets. So then I put 1 in here, plus 1 in here, and 1 in there. Okay, let's work it all out. So all I did was I calculated my numbers and I get 40. Now you can see there, I've just put that there because I made a mistake. So I didn't want to write it out again, but there it is. So I've got 27 plus 18 minus 3, and then this becomes minus 2, so I get a total of 40. Let's do another one. All right, here's example 2. We're going to evaluate the definite integral from 1 to 2 of 4 over 2x plus 1 cubed dx. Now, before we get started, let's just remember that we have this formula. If I have a linear function raised to the power of n dx, then my antiderivative is 1 over a, which is the coefficient of x in the linear function, divided by the new power after the power has been increased by 1, multiplied by this function to the power increased by 1, and of course plus c. So let's keep that handy while we work on this. So the first thing I want to do is I want to rewrite this so that my 2x plus 1, I can make clear what my power is there by writing it with a negative power. So I've got 4 times 2x plus 1 to the power of negative 3 dx. That's what I'm calculating. So my first step then is to anti-differentiate. So I'm going to keep the 4, and then I'm going to divide by a, that's 2 in this case, so multiply by a half. And I'm also going to divide by n plus 1. So if I increase my power, which is negative 3, increase that by 1, I get negative 2. So I'm multiplying by 1 over negative 2. Then I just keep the ax plus b, that's the 2x plus 1, and I raise it now to the power of negative 2. And my terminals are from 1 to 2. Okay, so this simplifies nicely. 4 over 2 times negative 2 will give me negative out the front. And then I'm going to rewrite this now with a positive power for my calculations. Don't have to, I just find it easier. All right, we don't need that anymore. Now we're just substituting. I'm going to put x is 2 into this expression, and then I'm going to subtract the same expression where x is 1. So I'm going to have negative 1 over, that's going to be 2 times 2 is 4 plus 1 squared, minus negative 1 over 3. Oops, yeah, let's call it 3 squared. So I'm going to have, this is going to be negative 1 over 25, and this will be plus 1 over 9. Oops, you can't see that. Which I went and calculated earlier, gives me 16 over 225. Should be able to do this by hand. Okay, it's a little laborious, but you guys can do that. Okay, so that's my second example. So that is how to use the fundamental theorem of calculus, how to use the right notation, and how to do the calculations. What we haven't looked at yet is what exactly that finds us, and we haven't looked at where that comes from. So the next video is going to go a little bit deeper into the theory of what is the fundamental theorem of calculus.